In this video, we're going to look at calculating hydrostatic force of a right triangular plate that has a base of 2, a height of 1, and submerged vertically in the water with the top vertex 3 feet below the surface of the water. So what's happening is we have this plate here, and it's got a base of 2 meters, a height of 1 meter, and it's sitting 3 meters below the surface of the water. Now, what we're going to do is calculate the hydrostatic force, and we're going to do it with our tried and true method of calculating the force on a slice. So let's take a slice here. Can be anywhere. There's our ith slice with a height of, we'll call it delta h. Now we got to decide how we want to measure h, and there's many options. It could be from the surface to here, it could be from the bottom to here, or I am going to choose this to be h sub I for my ith slice, and this to be b sub I for my ith slice. So I've got my drawing labeled, and you're going to see how these come in here in a second. The force on the ith slice is the pressure on the ith slice times the area on the ith slice. Now, the pressure on the ith slice is determined by its depth. And since we are in standard units, because we're given this in meters, and notice our density is in kilograms per meter, we have to multiply by gravity. So the pressure on the ith slice is going to be our density times gravity times the depth. So the depth, it's 3 meters plus another h sub I. So I think you can kind of see that here from the surface. The depth to my slice is right there. So I'm going to write that in as 3 plus h sub I. That's just the pressure on the ith slice. Now the area of the ith slice is a rectangle. It's b sub I delta h. Now the issue you probably notice here is I have two different variables, h and b, and we'd like those to be in terms of 1. Well, if I pull my drawing out, here's the plate, 2, 1, here's my slice, b sub I, h sub I. I've got similar triangles. So I can say that b sub I over 2 equals h sub I over 1. And solving that for b sub I get b sub I equals 2h sub I. So this is something that we've seen a lot in these sections. So my force on the ith slice, I'm going to put that in. I got delta G 3 plus h sub I times 2h sub I delta h. I'm all in terms of one variable. Now I can calculate the total force with a definite integral. I'm going to pull the delta and g out right from the beginning, and I have 3 plus h times 2h dh. Now let's think about what our limits are. H is just measured from the top of the triangle to the bottom with the way that I've described it. So h is going to range from 0 to 1. Think about it this way. There's only force on the triangle itself. There's no force that we're trying to calculate here. So we only care about calculating over the slices of the triangle, and because of how I defined h, my limits would be from 0 to 1. If you had h starting from the surface down, you would have been using possibly 3 to 4. So there's an infinite amount of ways to set these up, and your limits will correspond to the way you set up your diagram. So we have delta g, integral from 0 to 1. Let's go ahead and multiply. Let's even pull out the 2. We'll multiply that in later. 3h plus h squared dh. So 2 delta g, we're going to have 3h squared over 2 plus h cubed over 3 from 0 to 1. Plugging in 0 will zero this whole thing out, so we're not going to worry about it. So 2 delta g times 3 halves plus 1/3. So finding a common denominator, That's going to be, and multiplying by the 2, we're going to get 11/3. Our delta is 1,000. Gravity, we're using 9.8 meters per second squared. And so calculating this all together, we would get 35,933.3 repeating. And now our units, because we're in standard, is going to be newtons. So that's the total force on this plate.